We're actually going to be spending the next 3 lessons looking at application problems involving exponential and logarithmic equations and functions. And so what I want to do is I want to end this lesson with one application problem. If I sub 0 and I denote the intensity of light before and after going through a material, and x is the distance in feet the light travels in the material, then according to the Beer-Lambert law, negative 1 over k times the natural log of I over I naught equals x, where k is a constant that depends on the material. This might seem a little bit random and weird, but I want you to think about a lake. And so in this case, the material that we end up having is actually the water in that lake that I'm going to very crudely draw. I am not an artist, and the little highlighter tool is not very specific on here. But if you've ever dove down into water, or if you've gone scuba diving, you've probably noticed that the deeper you go, the less light gets through. And so effectively, what's happening is that the intensity of the light decreases as the light moves through the water. So this is what's going on in this situation. In fact, let's give some rays of light as well. We've read the problem. We don't need those words anymore. And I don't give drawings that often, so we might as well go all out. Let's give it a fish even. Super exciting. Anyways, let's take a look at this situation. So the first thing we're asked to do is solve this equation for I. Remember, I is the intensity of the light after going through the material. So our goal is to figure out how much light there is in the middle or the bottom of the lake. And to do that, we want to get I by itself. So we've got the opposite of 1 over k times ln of I over I sub 0 equals x. Now, if we want to get rid of this fraction, we can multiply both sides by k. But even more so, I want to multiply both sides by the opposite of k, because that's going to get rid of this fraction and the negative sign. So let's multiply both sides by the opposite of k. When we do that on the left-hand side, we notice that the negatives and the k's cancel, leaving us with just ln of I over I sub 0. And then on the right, we have negative kx. Perfect. Now that we've got the logarithm isolated, we can rewrite this in exponential form. When we do that, that's going to be e to the negative kx equals I over I naught. And if our goal is to solve this equation for I to get the I alone, we can do that by multiplying both sides by I naught. We can call that either I naught or I sub 0. Oops, it is the same either way. And when we do this, we get I alone, and I is equal to I naught times e to the negative kx power. So this is a way of rewriting that relationship where the variable I is solved for or isolated. All right, now let's look at the actual scenario here. For a certain lake, let's say that this constant k is 0.025, and the light intensity, I naught, is 14 lumens. This is how strong the light is when it hits the surface of the water. What we want to do is figure out the light intensity at a depth of 20 feet. So we want to know how intense the light will be after it goes through 20 feet. It should be less than 14 lumens because it's going to get less intense as it goes through the water. But let's actually figure that out. So we have I equals I naught times e to the negative kx. In this case, I naught, the original light intensity, is 14 lumens, times e to the negative k, which is 0.025, times x, which is 20 feet. And when we use a calculator to get an approximation, we see that this is approximately equal to 8.5 lumens, which is a little bit more than half of the original light intensity when it hits the surface. So when those rays of light go 20 feet through the water, they end up being just over half as strong as they were when they hit the surface of the lake. Now, why is this important? Well, when we're looking at bodies of water and the different organisms living inside, the biodiversity is affected because there are certain organisms that can only live in certain ranges of light intensity. There are some organisms that cannot have too much light. They'll actually die if they're exposed to too much light. And there are certain organisms that can't live unless they have a certain amount of light. And so if the light intensity ends up changing, if this lake, for example, undergoes some sort of change where the value of K is different because the water gets muddier or something happens that causes the water to change, then this value would end up changing, and it's possible that the biodiversity would change as well. Certain fish might live at different depths, certain bacteria might thrive or might die. So all of these things end up affecting what's going on in that lake, and we have a logarithmic situation that describes what's going on here.